At least when somebody comes later, they can be able to look at it. And the topic for today we want to understand is transmission impairment. And when we are talking about transmission impairment, we want to give an understanding of how transmission can be impacted. And it occurs when the received signal is different from the transmitted signal. So that is basically what we call transmission impairment. What was sent at the beginning is not what is received. And when that happens, it means that the transmitted signal has been affected in one way or another. And there is basically those three types of transmission impairments, whereby we talk of the attenuation, we also talk of distortion, and we talk of noise. So those are the three types of transmission impairment. Now, when we are looking at this, we are looking at signals that are being transmitted as either analog or digital signals, because in our previous class we said that signals can be transmitted as either being analog or digital. An analog signal, due to transmission impairment, can result in the received signal getting a different amplitude or the shape being different from the one that was sent. That is what we basically mean by the analog signal being affected. Because, for example, if we might just look at the signal, the way it normally looks like, let me open this one. So when we are talking about signals, we normally say that they can either be analog or digital. Analog signals, they have this infinite number of values in range. Digital signals can only have a limited number of values. And when we are presenting them graphically, this is how they look like. We usually have an analog signal that looks like this, and it has these three properties, whereby you're going to have the sine wave having an amplitude, that is the height of this waveform, and then it moves in time. So there is the aspect of height, which we call the amplitude, and there is the aspect of time, which now gives us the frequency, or how many cycles can the waveform make in a given period of time. And then there is what we call shift. How is the degree of this waveform from or in comparison to the 90-degree mark or to the zero mark here. So there is going to be a degree. It could either be 30 degrees, 45 degrees, 90 degrees, or any other value that can be showing the shift of the waveform. So those are the three properties which we normally use to show how the analog signal moves. Then the digital signal, like we have said, it is going to be having discrete values. And these values, it can either move from the positive side to the zero mark, and then over a period of time, it is on that zero mark, and then it also shifts again. So that is why it has a limited number of uh, values. Then, when we are looking at those periodic signals, we normally say that the periodic analog signals can be classified as either simple or composite. And when we are talking about a simple analog signal, we are saying that that same sine wave cannot be decomposed into any simpler signals. Like that is the most simple it can be. Then in a composite signal, we are saying that the periodic analog signal is composed of multiple sine waves. And then those can be showed here. So this one, it could be the simple sine wave or just basically the sine wave, whereby we have said that it is going to have the properties of amplitude, that is the height. It is also going to have a property of time, and it is going to have a property of shift, those three. So if you look at these two, one has a very high peak amplitude, the other one has a very low peak amplitude. That is how they can be different. So they might have the same phase and the same frequency, but different amplitudes. So if you want to know how you're going to calculate the frequency and the period, they are inverse of each other, whereby we say frequency is equals to 1 over the time being the period it takes, and time is going to be 1 over frequency. Then this is how we are going to show them. Again, here we have two signals. They have the same amplitude and the same phase, but different frequencies. When we talk of frequencies, is like how many cycles are going to be there in like a second. So here you're going in 1 second, like here, the same in this duration of time, you're having one cycle. In a half of that time, you're going to have a cycle, meaning that in the same duration of time, this one cycle is taking place. In this waveform, you're going to have two cycles. And that is how they are going to have different frequencies. So here is going to be 6 hertz in 6 periods, that is in 1 second. The 12 periods are going to be 12 hertz in 1 second. That is how they are going to be different. And then the units of period and frequency, like we have said, they are inverse of each other. So as time is going to increase, also the cycles are going to increase. When we talk about time increasing, it's like 1 second, meaning that it is taking longer here to get 1 hertz. But then in a tenth, that is, in a millisecond, you're going to have more frequency here. And then in a microsecond, that is 10 raised to the power of -6, you're going to have more frequencies, that is 10 raised to the power of 6. And that is how they go inverse with each other. And an example has been given here, like the power we use at home has that frequency. The period of this sine wave can be determined as follows, and it has been shown in that example. So that is something you can look at. So that was just a refresher showing how these sine waves are normally created. So let's go back to the lecture that we were having, and we discuss about transmission impairment. So I'm sharing this presentation on transmission impairment. I hope it is visible. And so we have said when as an analog signal is going to be transmitted, it can be affected by those three types of impairments. And we have the noise, the distortion, and attenuation. In the case of a digital signal, at the receiver side, you can get changes in bits. And when we are talking about changes in bits, you could have sent a bit being a 0, but when it gets to the receiver, it is a 1. That is where change in bits comes in. And that is how in analog signals that can be caused. So I hope up to there we are clear. And those are the three types of impairments that we normally have. So let us look at each one of them. When we are talking about attenuation, it means loss of energy. That is, the signal is going to lose power when it travels through a medium. And so when it loses that power or it loses energy, it is because it is trying to overcome the resistance in that medium. It could be in a cable or it could be in the open space, that is wireless transmission. And that is why we are saying that with increasing distance, then there is the cause of loss of energy so that you can overcome resistance of the medium. And that is why we say the signal has been attenuated. In order to address this problem, then we normally use amplifiers. These are signal regenerators. So they are used to amplify or to regenerate the attenuated signal so that it can be given more power or it can be given more energy for it to be transmitted a longer distance. So that is how it is done. So by attenuation, then you can always regenerate that signal. Then we continue, or before we get there, just to explain that a little bit better, because when we are talking about the signal being attenuated, it is very important to understand how the attenuation takes place, and also how it is usually resolved. So if I start a new slide there, and then I show you how the signal would look like. So the original signal looks like this. Through the transmission medium, it is going to get from point 1 to point 2, and because of distance, and it is trying to overcome the resistance in this transmission medium, then it is attenuated. You see, the amplitude has gone down, so it means that it is losing power, because when we are talking about the height of the signal, it is the amplitude, and that height is normally voltage, which makes it move like that. So it will go through this electronic or the signal regenerator so that it can be amplified to the original signal that it was, and it looks like that. So attenuation can be measured in terms of decibels. Decibels is either the loss or gain of energy, and we use this the term decibel to show. And decibel is calculated in this formula: 10 log base 10 P2 over P1. P1 being the input signal, P2 being the output signal. So that is how it is done, and it has been shown here where we have the amplifier, and then the point 3 can show that. So here's an example where we are saying, suppose a signal is traveling through a transmission medium and its power is reduced to 1/2. This means that P2 is a half of P1. In this case, the attenuation is going to be calculated this way in order for you to get negative 3 decibels, meaning that you have lost 3 decibels, which is equivalent to a half of the power, meaning that the signal was sent having 6 decibels. Hope up to there we are clear. And this is properly understood. Then we can also have another example here where we are talking about a signal traveling through an amplifier and its power is increased 10 times. This means that P2 is equals to 10 times P1. In this case, the amplification is going to be calculated as this: 10 log base 10 P2 over P1, whereby we are saying 10 P1. Then you have it as being 10 decibels. So there is also another one here whereby you can look at it to show how these ones are normally done. So these examples are there for you to look at and see how attenuation can be addressed. If there is a problem, we can discuss it together. Look at those problems. Then we have distortion. When we are talking about distortion, we are talking about a signal whereby a signal is going to be composite. And we have said that a composite signal is where you are having more than one signal, or a composite signal is one that has many other signals within itself. And so that is where distortion can take place, whereby a signal or a composite signal is going to have various frequency components. Like if you are saying you have one signal that has many other sub signals within itself, it means that they can only be separated by having different frequencies or different amplitudes or different shifts or phases. So that is where we are saying that these signals that are having different frequency components, each frequency component has some time constraint which makes a complete signal. So while transmitting this composite signal, if there is a certain delay that happens between the frequency components, then there may be a chance that the frequency components will reach the receiver end with a different delay constraint from its original, which leads to the change in the shape of that signal. The delay happens due to environmental factors such as the distance between the transmitter and the receiver, or other factors such as power. So that is where we are going to have that difference, and that is why we are saying that each frequency component has its own propagation speed when it is traveling through the medium, but then those different components can arrive with different delays. So if it was sent with a certain delay at the beginning, but it has been affected by an environmental factor, like the medium resistance or something like that, it means that it is going to have a different phase when it gets to the receiver from the one it had at the beginning. So this is how the distortion is going to occur. Here we have this original signal that has other subsignals, because there is this big one which moves like that. And within this big one, we have this small one up here. We have this small one here. So it's like you're carrying several signals within one big signal. So that is the composite signal that is moving. That is why you're going to have the big one, then the smaller one, and then the smallest one. These three are making this one big signal. Because of environmental factors, then they are affected somehow. So that the big one has gone like this, the small one like that, and the smallest one that way. Such that as they are getting to the receiver, the one which was constant here has been stretched a little bit here. Maybe its amplitude has gone up a little bit. Also here it has gone down a little bit. And here the frequency has changed a little bit, not like it was in the beginning. So it means that the original signal has been distorted. And once it has been distorted, this is the resulting signal that you get at the end. And that is where the big problem comes in with distortion. Then we get to the last type, which we call noise. And when we talk about noise, we normally say that it is one of the major factors in affecting transmission or bringing about distortion. Although it is of its own type, it is actually a contributing factor into bringing about distortion. And noise is defined as any unwanted signal that gets added to the transmitted signal, by which the resulting transmitted signal gets modified, and at the receiver side, it is difficult to remove the unwanted noise signal. So that is what we mean. Any unwanted signal. When we are talking about noise, we talk about it being any unwanted signal that will be added to the transmitted signal, by which the resulting transmitted signal gets modified, and at the receiver side, it is very difficult to remove the unwanted noise signal. And so when we are talking about noise, then there are several types of noise. We usually have the thermal noise, whereby these are random noise of electrons in the wire creating an extra signal. So especially when you are transmitting through a cable, and maybe this cable, you have put it together with the wiring cable. So this cable is for transmitting data, but you are using the same trunking to have the data cables together with what are they called? Electricity cables. It means that there can be some electrons. If power had a surge, meaning that more power has come into the cable, there could be some extra electrons that are thrown off, and they might affect the signal that is being transmitted in your cable. Because we said that when you're transmitting data through cable, that is digital data, it is going to be converted into electronic signals. So when you add an extra electron into the signal, it is going to create an extra signal, and that is what brings about thermal noise. Then we have induced noise, and this noise comes from motors and appliances or devices that act as transmitter antenna and medium as receiving antenna. So imagine you are talking about transmitting wireless data. And normally when we are doing a wireless transmission, we can do it using the base stations or the transmitters that we put on top of buildings, and they are able to send data and connect to another one at another point. In between, there could be some devices, either motors or appliances or devices that have transmitting antennas, meaning that they are also generating some kind of energy or some kind of electric or electromagnetic um, waves. When they generate those, they might affect the signal that you're transmitting, and that brings about the induced noise. Then there is crosstalk. When we are talking about crosstalk, is where you are having many cables which are transmitting. So when they are transmitting, it means that transmission from one cable may get to the other cable. And that is where we are talking about crosstalk being the same as induced, but with wires. So induced is with wireless, whereby we are talking about sending and receiving antennas or some kind of transmission in between the sending and receiving antenna. There is also some other transmission that will be happening. That is where induced noise comes in. So when we are talking about crosstalk, it is two transmissions in two different wires, but they are interfering with one another. That is what becomes crosstalk. And then there is also impulse noise, which comes from power lines or something to do with lightning. So it could be something which is natural or power lines which are interfering with the transmission that is taking place, or another introduction. That is why we call it an impulse. Another introduction of electromagnetic wave which is induced or comes as an impact to the current transmission, whereby transmission was taking place normally, and maybe it was raining, and then lightning strikes. When it strikes, if you don't have an earth, then that electric current or that electromagnetic interference will get to the cable that is transmitting your data, and it will introduce an extra signal that affects the transmission you are making. And that brings about impulse noise. So here we are showing this is the original transmitted signal, and then during transmission in the transmission medium, another signal is introduced. So it could be coming from thermal-induced crosstalk or impulse. Once it is introduced, it affects this original signal such that it will be received looking like this. And that brings about the problem we are talking about, which we are calling noise. So in order for us to understand if transmission performance is okay, we normally do it using signal to noise ratio. So that is trying to measure, or signal to noise ratio is a system of measuring how signal strength is in comparison to the noise in that transmission system. So you just want to see, is my transmission system okay, or is it affected by noise? That is what brings about the signal to noise ratio. So it is the ratio between the two powers, because the transmission power is still power, but the noise is also some power which is introduced into the normal transmission. So it is also measured in decibels, but now it is being referred to as SNR dB. So how do you calculate it? Here is an example. The power of a signal is 10 megawatt or milliwatt, and the power of the noise is 1 of this watt. And then what are the values of SNR and SNR dB? So how do you get that? Signal to noise ratio is going to be calculated by having the noise which is introduced over the power of the signal, which is down here, and you're going to get it as 10,000. Then this signal to noise ratio is going to be multiplied with 10 log base 10 for us to get it as being 40. So that is an example showing how you can get the signal to noise ratio. And another example there shows another explanation of signal to noise ratio, whereby we are saying the values of signal to noise ratio and signal to noise ratio dB for a noiseless channel are, since it is noiseless, it means that the signal power is going to be divided by 0. And when you divide it by 0, you always get infinity, because any number divided by 0 gives you infinity, or it is going to be indivisible, or it is going to be 0. So this is something we can never achieve because it is not ideal in normal life. In normal life, when you are transmitting, there are also other transmissions that are taking place, if not other causes of nature. And that is why it is difficult to achieve that. And then this is how it is shown, whereby you have a signal to noise ratio which is big and a signal to noise ratio which is small. So if it is big, then you're going to have the signal affected that way. If it is small, the signal is going to be affected that way. So that is how noise affects transmission.